Hi everyone, it's a pleasure to be here in Arc, so thank you for inviting me. Sorry.
So I'm just going to make a quick
introduction.
So yeah, we have the last conversation by John Veitch. So who is a senior lecturer in the Institute of Gravitational Research in the School of Physics and Astronomy at the University of Glasgow. And his research focuses on the analysis of black holes and neutron star collisions detected by gravitational wave observations such as the Advanced LIGO or laser.
Thanks very much. So as you heard, I'm John Veitch. Oops, gotta go to the next slide. There we go. So I mostly work on these topics here. I started off life as a physicist. I seem to turn myself into an astronomer, but actually I'm very interested in data science as well. So it's kind of a good place to be at the moment. Here's a picture of me at the LIGO Livingston Observatory, which is one of these gravitational wave detectors that you heard mentioned. Probably useful for those of you who aren't familiar with them to look at a picture. So this is actually the other one in America. One is in Washington State, the other one is in Louisiana at Livingston. This one is the Hanford Observatory. You see it's a gigantic lab that's in this L shape, where the arms of the L are 4 kilometers long. And the purpose of this is to measure ripples in the fabric of space-time, as we like to say. So we do that by measuring the length of these arms to extremely high precision. And as a gravitational wave comes by, it changes the length of the arms. I should say that in order to build a lab such as this, you need somewhere with extremely cheap land. So you can see that Livingston Hanford here is surrounded in this beautiful radioactive desert where they built the atomic weapons in the Second World War. And the US government had a lot of land going very cheaply. So it's quite an interesting place to visit if you ever have the opportunity. And there is actually a visitor center there. Okay, so blowing that up into a cartoon, what's going on inside that L? You can see now our arms have been compressed enormously. As a gravitational wave comes through, it's actually stretching and squashing space in these two orthogonal directions. So what we're measuring is the effect of the wave on the difference in the length of the arms. Now, this is a pretty standard technique in laser physics, interferometry. It's very often used for length sensing and so on. What makes this special is the enormous precision. So this diagram here is scaled up by, well, this number of zeros with 1 at the start times in order to show you what the effect of the gravitational wave is. But the actual waves themselves are unimaginably tiny, and the effect is extremely difficult to measure, which is why it was only in 2015 that it was first actually done. So gravitational waves themselves, let's say they're ripples in the fabric of space-time. That means gravity in physics is understood as being linked to the geometry of space in the modern understanding. So a gravitational wave is just like a light wave. You know, a light wave is a ripple in the electromagnetic field. If the gravitational field is the geometry of space, then a gravitational wave is a ripple in the geometry of space. So it changes the length of everything that it passes through in this way that's illustrated by this ring of test particles on 3 dimensions by this kind of worm thing. This is the gravitational wave passing through this region of space. And they travel at the speed of light, it's just like light waves. I can talk to you about the mathematical details at length if you're interested. You can come and find me at lunch, but we'll just move on. Always good to show a movie. What actually makes these gravitational waves? Well, you can't make them in the lab because gravity is really weak. You need an extremely strong gravitational source. And the only ones that we're able to detect at the moment are mergers of black holes and neutron stars at astronomical distances. So here's a movie of 2 black holes in a close orbit. And as they are orbiting around each other, they're losing energy, and eventually they collide to form, well, a bigger black hole, unsurprisingly. But the process of that is extremely interesting from a physicist's point of view, because this is really the only way that we can measure what's going on in the strong field regime of general relativity. Gravity is very weak on solar system scales and so on. Okay, so what's the signal? What's the data that we're looking at? We're here to talk about data science after all. It's actually audio waves. Turns out the frequencies that black holes produce when they merge stellar mass black holes at least. You could hear them with your ears if they were about a billion times more sensitive than they actually are. So that laser interferometer that I showed you, the 4 kilometer long thing, is really the world's most sensitive microphone. It's able to pick up these tiny little vibrations that are traveling in the gravitational field along through space. Okay, so these two black holes coming together, orbiting around each other, eventually they form a big black hole. And by looking at the shape of the wave, we can measure what the masses are of black holes that generated that wave. We can learn a lot of stuff about the spins of those black holes, where they are, and probe the fundamental physics that's taking place in this type of analysis. Unfortunately, because the signal's so weak, as I say, here's the strain is 10 to the minus 21. That means that the change in the length of those arms that are 4 kilometers long is about, well, it's actually slightly less than the width of a proton. So we're measuring a 4 kilometer long object to the precision of nuclear physics scales. In doing so, you can see the effect of the wave here, but there's a lot of noise left over because we're really operating at the very thresholds of sensitivity at this point. So in order to extract the information from this noisy data, we use the astronomer's kind of favorite technique, which is Bayesian inference. So a couple of facts about the black holes, I suppose. The signal to noise ratio is 24 for this, which is actually the loudest one we've seen. There are many more that are even closer to the threshold of detection. That's not a high signal to noise ratio by anyone's standards, I don't think. But this process is actually very energetic. In this wave, there's roughly equivalent to 2 times the mass of the sun times the speed of light squared in terms of energy that's being radiated by this process. So it's really interesting physics if you can see it, which we only really just can. Okay, so that was the very first one. We've now seen around about 100 of these things over the last 7 years now. And that number is ever increasing, and it's increasing faster and faster because the instruments are improving all the time, thanks to the efforts of my colleagues in the lab at Glasgow and elsewhere. Okay, so the information that we're learning, I won't dwell on this too much. I said we can learn things about the masses of the black holes, several times, 10 times the mass of the sun. The distance, this one was at about 450 megaparsecs, which is in a nearby galactic scale. And the position on the sky, which is useful if you look pointing a telescope to see if there's anything else out there. But there's lots more that we can measure as well. Okay, so there's Bayesian inference. I probably don't need to tell you how exactly that works. But what we're interested in is finding the parameters of that system, which you can write down as a probability distribution over the parameter space. And we're also interested in this normalization constant that you get. This is the posterior probability distribution. That's your likelihood function. That's kind of your forward model. Tells you what the data should look like if you assume a certain set of parameters. That's your prior, and then this is your evidence. This is useful if you're comparing different models, say different models of gravity or different models about the physics that's going on in the merger, which is something that we're very keen to do. So we actually kind of want to know what the evidence is, what's the normalization constant in this posterior probability distribution. So to get that, you have to do this integral of the likelihood times the prior over 15 odd dimensions of the model, plus all of the other dimensions that we've added on because we don't really know what the noise of the detector is like. So there's lots of nuisance parameters as well that we have to add on to the model. So we're kind of do a high dimensional integral, well, not that high by today's standards, but the model is very nonlinear. So it's a difficult problem to solve using traditional Bayesian inference, MCMC, and so on. So what we actually do is nested sampling, which maps this 15-dimensional parameter space into just one dimension, which describes the fraction of that prior. So if you imagine this box as the whole parameter space, you could draw a contour around the whole box, and that would enclose 100% of the probability. You could draw a contour here, and that would enclose, let's say, 90% of the probability, 80% of the probability, and so on for different contours. So if you can think about a label that labels the contour, if you integrate the fraction of the space that's contained within a contour times the height of the contour, then it's another way of getting that integral. So we're mapping a high-dimensional integral down to a one-dimensional integral that we can do. That's the nested sampling algorithm. It's very clever. If you didn't understand that, I can show you in the form of a movie, which is always better. So we take random samples and we eliminate the ones that have a bad fit. And as we do that, we get more and more concentrated set of samples, and we're walking uphill finding the peak. But we're not just interested in finding the peak, we're actually interested in the integral under this curve, if you like. So that's great. I mean, it's a fantastically useful method, but you have to be able to draw those samples within the contour. Not so hard in this toy example because it's got circular symmetry, so you could directly generate those. If your model is highly nonlinear, as ours is, you don't know what those contours are going to look like. There's no way of solving it. So you have to use something like MCMC or rejection sampling in order to get the next point. So that's where machine learning comes in for our current research. So all of what I've described up to now is kind of like what we have been doing. What I'm going to talk about now is what we're working on and what we're proposing to use going forward. And it's based on normalizing flows, which are a machine learning technique that's, Chris described them a little bit as being related to the invertible mappings that they were using. So basically, we want to learn these contours and we can map them using a normalizing flow, bijection, into something simpler that we can directly sample. So I can show you that cartoon. We're taking something complicated, this is only in one dimension, and we're applying a series of transformations to map it to a nice, easy Gaussian that we can sample with no trouble at all. The problem is that we have to learn what that mapping is. So we're using a normalizing flow, which is made up of a sandwich of layers, much like we heard about before, where you have a simple affine transform layer, that's a scale and a shift, followed by a permutation of the variables, and then another affine transform layer. If you sandwich enough of these together, you can reconstruct all kinds of functions. Although in our experience, there's actually, it works best when the series, when each layer describes the kind of symmetry group of the parameter, if you like. So if you have a periodic parameter, it doesn't do a very good job scaling, shifting it along and scaling it, because that's not the natural set of operations to apply to an angle. We want to apply rotations in that case. So we're working on how to improve that with a better learning of the signal manifold. There's some other independent work on that as well. So in doing all this, we can learn the contours, we can map them to something we can sample effectively. A few numbers about the problem. The amount of data that we're analyzing per likelihood is on the order of tens or hundreds of thousands of data points. Each draw of likelihood function, each simulation takes, on a good model, a fast model, it takes about a millisecond. So you can afford to do 10 to the 6, 10 to the 7 of them in your analysis, which is what we were doing 2 or 3 years ago with our old MCMCs. But with the more sophisticated models, they can take a second, even 2 seconds to generate a waveform for a binary black hole merger. And that just isn't going to work if we have to draw 10 to the 6, 10 to the 7 of them to do the analysis. So we're trying to reduce the number of times we call this model function by using machine learning to make the sampling more efficient. And you can see, well, this is our first version of this, our first proposal. State of the art was shown in blue, our result shown in orange here. So, we're getting a factor of a few speed up over the state of the art, which can actually translate to tens or hundreds of thousands of dollars worth of computing time when we're talking about the electricity it takes to do these analyses. So this is good. But we can do better, because if we break down the costs of this analysis, excuse this word flowing under a pie chart, most of the time is spent in the likelihood function, which is what we want, because we want to eliminate the overhead. But there is still quite a bit of rejection sampling overhead. There's some training time in the model. So we thought we could do better than that. So recently we've been working on an extension of this method called importance tested sampling. where instead of drawing contours and sampling a new point, we want to batch that. We want to draw entire distributions and sum them up to approximate the final answer. So again, I'll show you with a movie. So instead of drawing new points here, we're drawing new sets of points, new distributions. And our final answer is just given by a superposition of all of these things. And we found that this works incredibly well. It's not only much faster, as you'll see here, we're now beating the state of the art by about 10 to 20 times, and that's actually just got better. We found the body of the code. But this is actually giving us a really accurate measurement of the evidence as well. That's maybe an equal number of times better than what we've been able to do before. So that's quite important when you want to get precision results on some of these astronomical models. You don't want your code to dominate your source of error that you spent millions of dollars building an instrument to make the measurement in the first place. Okay, so I'll wrap up. This is just another breakdown of the costs, but too interested in that. I'll show you how it compares just to prove that it works. So we've got our previous state of the art in blue, and then our work in orange and green. And you can see that we're able to perfectly reproduce the more expensive Bayesian techniques that have been used up till now at a cost that's 10 to 20 times lower. So it's going to be really important because in the next 5 years, we'll have the final versions of advanced LIGO that'll be detecting thousands of signals. So running these analyses is going to cost tens or hundreds of times more, just because the number of signals that we're detecting. And then in the next 10 to 20 years, we'll be looking at new types of instrument that are able to see much further back into the early universe when all these black holes were being formed in the first place. So there's a lot of computational challenges that are on the horizon in this field, and machine learning is one of the techniques that's particularly exciting to try and overcome these hurdles. So I've been showing that this is the increase in the number of signals at the moment. This is going to get even steeper. We're all eagerly awaiting the next observing one, which starts early next year. Okay, so I'm going to wrap up just by giving you an advert. If you have a Bayesian inference problem to solve, and if you're especially interested in finding the evidence, then go to this URL and you can download the code. It's very easy to use. It's all based in Python, as a lot of things are, so you can install it and so on. And I'm very happy to talk to anyone at lunch break. If anyone wants to have a look, I'll be happy to give you a tour. Okay, thanks for listening.
Thank you very much. Does anybody have any question in the audience about this topic?
Yeah, I was just wondering, have you looked at diffusion models at all? And if they're interesting relative to normalizing flows for them?
I think I may be getting jargon mixed up. There's a thing called diffusiveness of sampling, but I think that's different from what you're asking about.
Yeah, so a lot of the recent image generation stuff use these diffusion models, so they implicitly represent.
Oh yeah. Okay.
I know you're particularly interested in integrating constants, maybe not there.
I've not looked at those. I have a question about that then. Is like one of the problems that we have is that there's only maybe a couple of thousand points to train on to try and learn the shape. So we're kind of data starved. So we're looking especially for techniques that can operate well on a small batch of data. I don't know if that's the case with diffusion models, maybe it is.
We have a poster about diffusion model, maybe not for gravitational wave, but
yeah.
I also had a question maybe, which is like usually like when we ask whenever we're doing Bayesian inference, it's like the influence on the prior that doesn't end the prediction. And if you're considering maybe estimating like the mass of the black holes that are merging with the different centers, and say they give you like different means and confidence intervals, how can you judge which one would be actually closer to the ground truth, or is it possible at all to do?
Well, different samplers should give you the same answer if they're applied to the same model. So that's one thing we do. We cross-check different samplers so we know that they're quite fragile. But I think the general picture is like, what's the effect of the prior? Well, we do a lot of hierarchical inference as well. The stuff I've shown you is kind of the first, technically the second step in the analysis that gets fed in to hierarchical Bayesian models. So they kind of tweak the prior to learn about, say, things like cosmological parameters and information about the binary black hole mass distribution and things like that. One of the things that I'm particularly excited about with this version of the code is that we've broken the link between the sampling the prior, which is part of Nessai sampling, and doing the integral. So now we can easily reevaluate that integral using the same data set without having to rerun the code, which was not previously possible. So we can get much better hierarchical inference results. That's an area that we've not actually explored yet, but I'm very excited about going forward.
Any other question? Okay, so thank you again, John.
Thanks very much.
So that's it for this session. So now we're going to have a 1 hour lunch and poster break. We can also ask again our speakers if you have other questions. And